Hello, in this video we are going to learn how to predict the structures of unknown organic compounds. For example, let us look at the structure of nicotine over here. This compound is obtained from a tobacco plant. It was first isolated in the year 1828, but the structure was not determined until 1893. That is about a century later. However, after the structure was determined, the synthesis was able to be achieved for the first time in the year 1904. With the current techniques and the innovations, we can be able to develop new compounds and synthesize them within a matter of days. How then do we achieve that? Well, we can first of all analyze the molecule and determine the degree of unsaturation. And this we can use the hydrogen deficiency index to calculate the degree of unsaturation. Alkanes are known to be fully saturated, and they have the formula CnH2n plus 2, where N tells us the corresponding number of the atoms. If we compare this alkane over here and the alkene, what you notice is that the alkene here is lacking 2 hydrogen atoms, which is 1 molecule of hydrogen. So it has -1 molecule of hydrogen. The alkyne is lacking 2 molecules of hydrogen. So we can use the hydrogen deficiency index to tell us the degree of unsaturation. So this alkene here has 1 degree of unsaturation. The alkyne has 2 degrees of unsaturation. So in other words, 1 unit of hydrogen deficiency index equal to 1 degree of unsaturation. We can calculate the hydrogen deficiency index using the formula HDI equals to half into 2C, where C is the number of carbon atoms, plus 2 plus N, where N is the number of nitrogen atoms, minus H, where H is the number of hydrogen atoms, minus X, where X is the number of halogen atoms. From the structures, you can notice that we treat a halogen as if it was a hydrogen atom, while we do not use oxygen in the formula because oxygen does not affect the number of hydrogen atoms. When an atom of nitrogen is used, it increases the number of hydrogen atoms by 1. Okay? Let us look at an example. Draw all possible structural isomers of C4H6. So from here, we can use the formula. Carbon atoms, we have 4, so 4 times 2 is 8 plus 2, we get 10. 10 minus 6, all divided by 2, that gives us 2. So with 2 degrees of unsaturation, we can develop a list of possible structures. And that list of possible structures could be, probably the compound could be having 2 double bonds, which could be isolated or cumulated, that is, they are connected, that is close to each other. Or the compound could be containing 1 triple bond, which could be in a terminal position or in the internal position. Or it could have 2 rings. Each ring counts as 1 degree of unsaturation. So here we have 2 rings, so that accounts for 2 degrees of unsaturation. Or we could possibly be having the compound being 1 ring and 1 double bond. determine the structure of an organic compound with the formula C6H12O. So again, by using the formula, we don't have any nitrogen or halogen here. We don't cater for oxygen in the calculations. We simply have carbon and hydrogen. So that is 6 times 2 is 12 plus 2 is 14 minus 12 all over 2, which gives us 1 degree of unsaturation. So therefore, we could have a double bond, we could have a carbonyl, which also has a double bond connection between a carbon and oxygen, or we could have one ring, which accounts for 1 degree of unsaturation, okay? Of course, plus others. But then the good thing here is that now we know that we are only going to consider structures that have 1 degree of unsaturation. So in other words, the degree of unsaturation does not tell us the final structure of the compound. So we need to accompany this using other strategies as well. So the other strategy that we could use to kind of limit us to the direction we're heading to is infrared spectroscopy, which can help us to quickly determine the appropriate functional group. The way we use IR spectroscopy is that the molecule is subjected to IR radiation. And when that happens, the molecule is going to experience what is called stretching vibrations. The stretching vibrations can be translated into an IR spectrum. So this is what we call an IR spectrum. Within the spectrum, the vibrations are translated into signals that can help us identify the functional group. So we have what is called the wave number, we have the intensity, we have the shape. So these are the signals, and those signals appear at specific wave numbers, okay? They correspond to specific wave numbers. And the shape is also unique to each functional group. So within the IR spectrum, from the region of 1,500 going to around 400, we call this portion the fingerprint region. From here, going all the way to this other side, we call it the diagnostic region. It is the diagnostic region that we are going to focus on at this moment. The diagnostic region is going to help us identify the functional group, okay? If we cannot tell the differences within the diagnostic region, then we might go to the fingerprint region, but there are a lot of things going on usually in the fingerprint region. So right now, our focus is going to be in the diagnostic region from 1,500 all the way to around 4,000 wave number. That is over here. Now, how do we use the wave number, the signals, and the intensity to help us identify which functional groups are present? So for alcohols, they usually have a broad peak. So this peak is considered broad peak, and it appears at a region of between around 3,400 to around 3,600. The primary amines, that is a nitrogen connected to 2 hydrogen atoms, will show 2 peaks within the same region of between 3,400 to around 3,600. But they are not going to be intense. So we can say these ones are less intense. They are slightly broad, they're not very sharp, so slightly broad, but they're not intense. and here we see that there are 2 peaks. For a secondary amine, the one that has 1 hydrogen atom, what you see here is 1 peak that is also less intense, but within the same region of around 3,300 to around 3,500. Another region that we're going to focus on is between around 1,600 to around 1,800. In this region, we will be able to find the double bonds. So the double bond could be an alkene or it could be a carbonyl. So carbonyls have usually intense peak. So an intense peak that is prominent. For the alkene group, the double bond, it's usually less intense. Okay? And then the other key area that we will be focusing on is the region around 3,000. Okay? So note this red line. Note this red line here. So we look at what is happening below 3,000 and above 3,000. So we're going to focus on these areas, below and above. So for alkanes, we will experience these peaks that are below 3,000. That means the compound is going to be sp3 hybridized, so that the hydrogen here is in an sp3 hybridized carbon. If the hydrogen here is in an sp2 hybridized carbon, then the peak will appear above 3,000, usually at around 3,100. Around 3,100 wave number. Okay? If it is sp hybridized, the peak will usually appear at around 3,250. So roughly more than 3,100. So then we're going to have an sp hybridized carbon which has a proton connected to that carbon. So in other words, we can be able to identify if an alkyne is present, if an alkene is present, if an alkane is present, if we do have a carbonyl, if we do have an alcohol, if we do have an amine, which could be primary or secondary. Okay? So let us look at the general analysis of an IR spectrum. We have said that you need to focus on the region above 1,500. So from 16 to 1850, look for double bonds. Okay, carbonyls, alkenes, all the double bonds. Okay, within the region of 2,100 to 2,300, look for triple bonds. This could be triple bond composed of carbon-carbon. It could be nitrogen. So you look for triple bonds within this region between 2,100 to 2,300. Between the regions of 2,700 to 4,000, here we're going to look at a variety of them. We could look at the amines, like primary amine, secondary amine, the alcohols. We can look at the alkenes, alkanes, alkynes. Okay? Then we need to analyze the wave number, the intensity, the shape, so we can be able to account for the functional groups that are present. All right? And it's time to do some practice exercises. Predict the structure of C5H8O2. In this case, we already have a list of possible structures. We just need to match the spectrum to the appropriate structure. Now, by looking at the structure, we can tell that there is a carbonyl because of the intense peak at around 1,700. If we draw a line at 3,000, straight line, Let's make it straight, like that. We can tell that there is no alkene or alkyne, because what we see from here implies that there is only sp3 hybridized carbon. Okay, so because of sp3 hybridized carbon, we only have an alkane. Now that is all we can get from here, nothing else. So that means any alkene is out. And now we are left with two choices, either the carboxylic acid or the ester. What you need to know for carboxylic acids is that they have a unique signal in the IR spectrum. The signal usually begins from around 3,300 and it goes all the way to around 2,500. It is not broad peak, neither is it a smooth peak, but anytime you see a peak like that, that's a signature for a carboxylic acid, which means that the compound that is represented here is likely to be an ester and not a carboxylic acid. Moving to the next one, predict the structure of C5H8O2, in which we have the spectrum shown over there and the list of possible molecules shown here at the bottom. Now, by looking at that structure and the description I just demonstrated in the previous slide, you can now tell what kind of peak this is. This is a signature peak for a carboxylic acid. So therefore, anything that's not a carboxylic acid, we exit out. So we do have three possible structures. Then we need to draw a line at 3,000 and see whether we do have an alkyne or an alkene. And here we don't have any peak beyond 3,000, so therefore it's going to be an alkane group, a hydrogen connected to an sp3 hybridized carbon. So that eliminates the alkene and we end up with the right product that matches the spectrum. Predict the structure of C5H8O2. Well, we can identify the carbonyl, and if we draw a line running through the 3,000, we can tell that we do have a functional group other than an alkane. So that means we do have sp3 hybridized carbon, we also have sp2 hybridized carbon. So there's a possibility of having an alkene. If an alkene is present, then it means anything that does not have an alkene is going to be out. Okay? So we do have carbonyl, which means that portion is out. We don't have a carboxylic acid because there's no signature peak like the one we had for carboxylic acid. So we end up with the right structure that we can predict to be the ester with an alkene portion. Predict the structure of C5H6O2. Now in this case we don't see sp2 hybridized carbon, so we can say that there's an sp3 and then there's a peak at around 2,300 or 2,250. So that means we have an alkyne. So all we can say is that there must be an alkyne. We don't know whether it's a carbon-carbon. So looking at the structure, we can tell that it's going to be a carbon-carbon. But we can also figure out that it's not going to be an sp3 carbon which is terminal, because if it is terminal we should be able to see the proton here in the 3,300 or 3,250 region. So we don't see that here, so therefore it's not going to be terminal. So we don't have that, we don't have that, we don't have that. So there are only two options. We do not have a peak, which is a signature for carboxylic acid. So it definitely tells us that the structure is going to be the one circled, where we can identify the carbonyl to be that one. Okay.